Hello, and welcome to this presentation on MSPTDfast, an efficient photoplethysmography beat detection algorithm. Photoplethysmography is now widely used in clinical devices such as pulse oximeters and consumer devices such as smartwatches. And yet, I don't think we yet have an open source algorithm for detecting individual heartbeats in the PPG, which is suitable for commercial use, of high performance, and highly efficient. To introduce myself, my name is Peter Charlton. I'm a biomedical engineering researcher at the University of Cambridge, and my colleagues and I are currently running a study looking at using wearables in screening for atrial fibrillation, where the detection of individual heartbeats in the PPG is a key task. And so today, the goal of this work was to develop an efficient open source PPG beat detection algorithm. In this presentation, I'll firstly summarize the state of the art on open source beat detection algorithms, and then I'll present our work on designing and evaluating a open source PPG beat detector. A couple of years ago, we assessed the performance of open source beat detection algorithms, and we found what we thought were the two highest performance beat detection algorithms assessed in terms of the accuracy of beat detection, QPPG and MSPTD. And so now, when someone asks what algorithm would you recommend for detecting beats in the PPG signal, these are the two options that I have in my mind. And they have different pros and cons. Both are openly available. QPPG is available under the GNU GPL license, whereas MSPTD is available under the more permissive MIT license, and so is more suitable for commercial use often. But on the other hand, QPPG is highly efficient, whereas MSPTD is less efficient. So after looking at this, we decided to try and improve the efficiency of MSPTD to develop a suitable implementation of a PPG beat detection algorithm. So how does the MSPTD beat detection algorithm work? Well, it works by calculating a local maxima scaleogram, which is shown in the bottom right of this image. And for each point on the PPG signal, for instance, the red point of interest, it does this by comparing that point to its neighbours, the two black points either side, and asking whether or not it's higher than those 2 points. If it is higher, then it populates this on the scaleogram with a yellow square, and it continues this process, increasing the scales from just one sample separation to multiple sample separation as we move down the scaleogram. And here you can see that this systolic peak is higher than most of the other points on the signal, so most of those points are yellow. In contrast, if we look at a point on a downslope, then here it is briefly higher than its neighbours here, but otherwise it's lower than one or other of the neighbours. So there's only that brief period, second brief period of yellow on the scaleogram. And then thirdly, if we now look at a diastolic peak, this is briefly higher than its neighbours, but then for the remainder is lower. So again, only has a short yellow period on the scaleogram. We repeat this process for all the points on the signal, and now we can see a blob corresponding to each pulse wave. Note, it doesn't work so well at the start of the signal. We can then identify pulse peaks by firstly identifying the scale with the most local maxima. That's the row that has the most yellow entries. And then identifying peaks as points, i.e. columns on the scaleogram, which are all local maxima up until that scale. So, designing and evaluating a refined MSPTD algorithm. We identified several potential improvements that we thought might be helpful for improving efficiency, and we tested this on various PPG signals. Here's an example on the right. Firstly, whether, as in the implementation of MSPTD, we need to calculate scalegram for both peaks and onsets, or whether we can get away with just calculating one scalegram or the other. Secondly, whether we could make the method used to calculate the scalegram more efficient by replacing the current nested for loops with a vectorized approach. Thirdly, whether we could truncate the scalegram to only use, for instance, scales corresponding to heart rates above maybe 30 beats per minute. Fourth, whether we could downsample the signal prior to analysis to reduce the size of the scalegram and still retain beat detection accuracy. And then fifth, whether reducing the duration of windows analyzed would improve efficiency. To investigate these, we evaluated the impact of each option for each potential improvement on the execution time and the F1 score. That's a combination of sensitivity and positive predictive value indicating the accuracy of beat detection. We then identified those potential improvements which reduced execution time whilst not substantially reducing the F1 score, and incorporated this into MSPTDfast. We then compared this MSPTDfast to MSPTD and QPPG, and this was all performed on the PPG Dahlia dataset, which contains wrist PPG signals from 15 young subjects during their lunch break. So the results. These are the plots for each individual potential improvement, and each plot shows two things. It shows the execution time in blue and the F1 score in red. We found that two potential improvements resulted in a reduced execution time whilst maintaining a relatively high F1 score. So looking at the top right, we found that using scales higher than 40 or 30 beats per minute reduced execution time compared to the original N/2 scales whilst maintaining F1 score. So we chose to only use scales corresponding to heart rates over 30 beats per minute. And then second, when downsampling the signal in the bottom right, we found that you could downsample to around 20 Hz without substantially reducing the F1 score, and that this would improve the efficiency quite greatly. So we used these two potential improvements in MSPTDfast, and when we now compare MSPTDfast in the middle to MSPTD on the left or QPPG on the right, we find that the execution time is now much lower than that of MSPTD. There's a minimal reduction in F1 score, and its performance is now somewhat comparable to that of QPPG. The algorithm is openly available, and we've provided instructions for how to reproduce this analysis, including a video walking the user through step by step. So, MSPTDfast reduced execution time by over 70% compared to MSPTD, whilst retaining beat detection accuracy. This was achieved by reducing the size of the LMS matrix by downsampling the signal, that reduced the number of columns, and reducing the number of scales over which beats are detected, that reduced the number of rows. So, have we reached the peak of PPG beat detection, or is this a load of rubbish? Well, let's look back at the methods. We only compared MSPTDfast to a couple of other algorithms, and in addition, when we think about the data used, we use the same data both to design and evaluate the algorithm, and that dataset was small, only containing wrist PPG signals. So we're now extending the work to assess performance on two independent datasets, acquired the first from critical care from both adults and neonates with finger PPG signals, and the second from adults undergoing a mental stress protocol with wrist PPG signals. And we've also compared the performance to several more state-of-the-art beat detectors. In addition, original implementation was MATLAB, and we're now working to implement that in a widely used toolkit in Python. So I'd like to thank my colleagues and funders and conclude by saying we've developed MSPTDfast, an efficient and accurate open source algorithm for PPG beat detection. It's available under the permissive MIT license. However, in an attempt to make it as reliable as a climbing rope, we're now publishing further results, implementing it in a widely used toolbox, and we should test this final implementation to ensure it's robust. Thanks very much.